Good day. On behalf of the Joint Industry Project on Corrosion Inhibitor, I would like to welcome you all to the webinar series, Precision in Corrosion Inhibitor Selection Testing for Oil and Gas Applications. Precision is the first right step. The objectives of this webinar series are twofold. First, to promote broader awareness across our industry on the need for developing standard test methods with published precision data for all our corrosion inhibitor evaluation and selection tests. We will also talk as to how the standard test methods are being developed. Just before the webinar, Jason was talking about potential collaboration with one of his new colleagues. That is very, very important. To develop standard test methods, the importance of collaboration and coordination cannot be specified. Very, very important. Once we develop the standard test methods, they will have huge impact in our industry. So that is the broader reason for this webinar series. And also, I'll talk about where we are with respect to the joint industry project for evaluating efficacy of corrosion inhibitors. And we started off the phase 3 yesterday. Phase 3's intention objective is to develop standard test methods for evaluating inhibitor efficiency and secondary inhibitor properties, especially to develop precision based on repeatability. So in our webinar today, webinar 3, I will share with you some of the case studies I was involved with or I am aware of on how people have benefited from the standard test methods with published precision data, as well as I will highlight some of the problems that arose due to the absence of standard test methods. Again, the driver for all these efforts is to fill the industry gap, that is to have quantitative criteria for evaluating corrosion inhibitor, similar to other corrosion control strategies such as materials, coatings, and cathodic protection. So we want to give specific guidelines, quantitative guidelines in the selection and evaluation of corrosion inhibitors. That is the primary driver. But today I'm going to share in this slide some of my personal drivers that motivated me towards precision in corrosion inhibitor testing. Let me start off with my PhD guide, Dr. Fred Pushpanathan, who introduced me to corrosion field in 1980s. Fred is a very interesting character. He's a very kind of dramatic person. He doesn't teach you anything. He doesn't guide you anything. He does things dramatically. So when I joined PhD with him, he asked me to do two things. He gave me 3 envelopes and asked me to deposit the amount in the bank. And he also asked me to do some corrosion testing. And he asked me to do the 2 tasks 3 times. So the envelope he gave me had 1,000 rupees in all the envelopes, and I deposited all the money he gave. And I was very proud of it because I was a young chap and I didn't know how to approach the bank and so on and so forth. I was very proud of it. But I was not comfortable when showing the data that I obtained from the corrosion testing. And I was explaining to him, look, professor, I didn't do something correctly. I got some variations. So let me redo the test. That's when Fred told, look, depositing the funds in the bank and doing corrosion tests are entirely different ballgame. When you do corrosion tests, you have to be confident in telling that you did have some variation. That was the very first lesson I learned from my PhD professor. The second character, again, he was Professor Venkatappa. He was a section head. He was one of the strictest professors I have ever met. Very nice person. In fact, he offered me to stay in his house for 4 years, but he's very, very strict. And everything people do, he make them to do 3 things. If you lock your lab, you will ask, did you lock it? Then you will ask, did you check it? Then you will suggest, go back and recheck it. Whether it's locking, doing the experiment, he always had the 3-step process. After suffering through these professors, I came to Canada through Dr. Winston Reevy, program manager, and he was the one who brought me from India to Canada. And I think most of us know Winston Reevy. Sometimes people say when you tell the name, it reflects on the person's character. So that saying applies aptly for Winston Reevy. If you look at his name, it is Reevy Winston. That means he's a person who reviews everything and wins in tons. When I worked with him for 20 years, every time, whether he gives a presentation or I give a presentation or anybody gives a presentation or any data, he asks us to review, repeat, and confirm that what we have got is correct. Winston is very, very particular about it, and that is one of his success stories, one of the reasons for his great success. Dr. Sheldon Dean has been a NACE and or AMP and ASTM member for more than 60 years. He is 92 plus years, and he is sharp as a gun. In fact, I spoke to him a couple of weeks ago. And Sheldon helped me to develop the standard test methods for ASTM, and he does it for everybody who is interested. So when I asked Sheldon how to proceed with the standard test methods development, he said you have to ask the labs to do the test, repeat the test. And he had 2 principles. First, he suggested that you perform the test in duplicate. That is, do the test twice. If the results are within 10% of one another, accept the data. If the results are not within 10%, then conduct 2 additional tests and calculate and report the average and standard deviation from all 4 tests. So in this process, initially we need to do only 2 tests to establish the repeatability. Alternatively, Sheldon suggested that you ask people to do 3 tests in triplicate and provide the average and report the average and standard deviation. When you look at all these 4 experiences from different folks, different guides, different gurus who guided me, the commonality is that they suggest that you repeat and check so that you are confident. That is precision. That is the focus motivation for the whole webinar series as well as for the joint industry project. Let us see one example before I start talking about the case studies. What are we going to do? We are going to establish precision. And how does it help? Let us assume that we are getting corrosion rate and we are also reporting inhibitor efficiency on a particular inhibitor over a period of 300 months. The first step is to understand what is the variation when we repeat a test under uninhibited condition. It is not a one value. Unfortunately, that is how Mother Nature has created. It is a range of values. That range is known as precision. Once you establish the range of a confidential level, then we can manage inhibitor program very effectively in the field. For example, in this case, the corrosion rate, general corrosion rate was between 20 and 25. That is the band, that is a precision. And when you do the corrosion inhibitor regularly, if the results are varying only in that band, and again, very low corrosion rate, high corrosion inhibitor efficiency, then the inhibitor is approved and continue to be used. If it is, as long as it is in this range. If it goes a higher range, then perhaps the field operator should talk to the vendor, hey, we are getting some variations. What is going on? So we need not have to bother about small variations, but the variations are too much beyond the boundary or the precision statement, then that will trigger an action. And suddenly, if the inhibitor efficiency decreases, then the field operator should inform integrity team. And if it is further, then the inhibitor program should be reviewed. So the precision statement helps not only during selection of inhibitor, but also during application of inhibitor in the field. So that way, precision is very, very important. With that, let me share with you some 7 case studies under 2 categories. How people benefit from standard test methods with published precision, and how things did not go well in the absence of standard test methods with known precisions. For all these case studies, I'm going to use 2 examples from ASTM. For those who are familiar with ASTM G5, which is the flagship standard test method published by ASTM, using this characteristics S curve is known for stainless steel in sulfuric acid. I will use this graph a little later to explain the importance of precision, but this was published almost 40 years ago by ASTM, and G5 is one of the flagship standard test methods. The second test method, standard test method, is ASTM G202, which is closer to our heart for inhibitor evaluation. This is the repeatability statement published by ASTM G202. Again, note here, the average in terms of mils per year is 23 plus 23.1 millimeter per year, 0.587. This is the precision, this is the variation by repeatability. If same operator does it, the repeatability varies by 4.7. Different operators, 5.4. This is the published data from ASTM 202. Again, note that the average remains the same, both in terms of repeatability and reproducibility. So I'm going to use these 2 examples in our case studies. If you are testing materials for implant in our body, then that testing protocol should be approved by, for example, Federal Drug Agency in USA. And the FDA encourages use of standards in medical device submissions. Before you submit a device for to be used in the health field, those technologies, whether it is a material or operation or a device, they must be evaluated based on published standards. And FDA gives a list of standards. And again, it's open in the public for US. And again, note that ASTM G5 is recognized. So only those devices or materials or the laboratories that qualify themselves using the famous S curve are allowed to do testing in the medical field. And this has been well established, practiced, so much so that some of the laboratories that do testing in the medical field will do the ASTM G5 almost every week, the first day of every week. That is a kind of rigorous enforced by the medical field. When I was working with Winston at Canmet Laboratories, before we let the technicians to work in the corrosion laboratories, we will encourage them to reproduce the famous ASTM G5 curve. As you can see that I shown 4 data points, technician 1, 2, 3, and 4. Technician 1 and 3 was able to produce the data that is within the ASTM G5. Technician 2 and 4 had some error. Basically, these 2 technicians did not take care of the apparatus properly. The connection was not made properly. The solution was not prepared properly, and deoxygenation was not taken care of properly. So this gives us a confidence that any lab data that was produced in the laboratory was performed by technician who first of all qualified himself or herself in conducting corrosion testing. And we used to encourage technicians to do this test every 6 months during our involvement in the corrosion testing laboratories. This is not universe. This is not unique to one sophisticated laboratories such as Canmet. This is another example. This is from Qatar. Mr. Abdul Bad made this presentation in one of the AST meetings. They also do the same practice. Again, this particular research institute is heavily involved in corrosion testing for oil and gas. For them, the technician should produce this curve. If they produce curves like this, the technician is not qualified. Not only technician, but also the instruments. So this famous S curve is universally used to qualify technicians in many parts of the world, especially for testing in medical chemical field involving corrosion resistant alloys such as stainless steel. Looking at this graph is a bit of confusing. So ASTM also put out the range at 4 potentials. If you get the current density within the range, then the lab is qualified. So that way, precision helps us to give us confidence in the data that we produce. Again, recollect that unlike depositing funds in the bank, when you do the testing repeatedly, corrosion testing repeatedly, they will show variation. We have to be aware of it. We have to report it. That's what the 3 case studies educate. The next case study is very dear and near to my heart. And many of you were aware of this issue. Around 2010s, some of the environmental groups aggressively promoted that the Canadian crude oil is extremely corrosive under oil transmission operating conditions. And they also kind of forced US not to buy Canadian crude oil. And fortunately, we had some good data, not only us, but different parts. But I was interviewed several times in the newspaper, and I made a presentation at the National Academy of Sciences Committee in Washington, D.C. And I also appeared in front of the Senate, the Canadian Senate, the Parliamentary Senate. And all these things are still available. And most of these interviews and the presentations were also referred to in
No, I got it.
some of the.
I'll delete that right now. January 19th. Oh, I think I did. I'll double check it. It's not there.
Krista, if you can mute yourself, that'll be great. Sorry.
Sorry, Sankar.
That's okay. Thanks, Krista. In all these presentations, all the interviews, I used only one graph consistently. Again, I went back to ASTM G202, the repeatability and reproducibility statement. This was developed using synthetic seawater in the absence of any crude oil. So this is the bottom line. And this is the test we did at 5% sodium chloride in the absence of crude oil. And I showed that in the presence of crude oil, the corrosion rate dropped tremendously. With this one graph, I was able to convince the politicians, the environmental group, the newspaper agencies. So that is the greatest merit of precision and bias, or repeatability and reproducibility statement. This particular graph was asked several times, did you produce it? Is it only your data? I said, no. This particular data was produced by 10 laboratories from across the world. So this particular bar was a savior in all our defense against some of the environmental group. So that way, precision in terms of repeatability and reproducibility is very, very critical. Let me also move on to another case study. This is one of the greatest, very reputed laboratories in one part of the world. And they claimed that they used ASTM G202. And they showed data by two operators in their lab. They said, we are getting results consistently. We are good. Then we challenged them with ASTM G202 with this reproducibility statement. Under the same condition, ASTM G202 reported an average corrosion rate of 23 plus or minus 5 MPY. In other words, you should have got result in the absence of corrosion inhibitor somewhere here, not 100 plus MPY. After lots of back and forth, we found that they were not deoxygenating the solution properly. There was a huge oxygen ingress, which increased the corrosion rate. Once we explained to them, based on the consistent repeatability and reproducibility data, they were able to redo the test properly, remove oxygen, and they were able to produce data that is plus or minus 27, which is within the range of ASTM. This is the merit of having published precision. It helps everybody in the long run. Now let us also talk about some of the issues that happened when we don't have precision statement, when we don't use standard test methods without precision. This data actually was published by Materials Performance, and Milan Bartas, I believe, is in the webinar. He was a co-author of this paper. We had 3 inhibitors, inhibitor 1, 2, and 3. It was given to 3 different laboratories, and they followed 3 different methodologies, A, B, and C. Lab A ranked inhibitor number 2 as the top. Lab B reported inhibitor 1 to be the top. Lab C reported inhibitor 3 to be the top. So now how do you select the inhibitor? So what's the purpose of doing the corrosion tests? So that is, again, we cannot technically define as to why one of the inhibitors was chosen. Because in the absence of precision, nobody can guarantee what they have produced. One more case study. This was shared to me by one of the chemical suppliers. Apparently, 10 companies, 10 chemical inhibitor suppliers were bidding for a project. And that particular owner operator asked them to submit their chemical to one of the chemical testing laboratories, third-party laboratories. And the third-party laboratory ranked this particular inhibitor, I, as number 9, lowest from the bottom. Obviously, that chemical supplier did not win the bid. They lost the bid. And they worked on the chemical for almost 2 years, according to the person who explained to me. So they were obviously were unhappy. So what they did was they asked the third-party laboratory again without telling them the chemical, and they gave the same chemical and asked the third party to repeat the test without revealing that all the chemicals were same. When they repeated test, the same third party ranked inhibitor 1 once, inhibitor 2 twice, second time, same inhibitor as rank 4. Originally, it was rank 9. Now, what do you do with this data point? Obviously, it leads to confusion. We cannot defend their action. That's why standard test methods with known precision will help us to give some kind of guarantee in terms of ranking corrosion inhibitors. To sum up in this webinar, developing standard test method with known precision is not a luxury reserved for sophisticated laboratories. It is a fundamental parameter that all laboratory operators, owners, operators, inhibitor suppliers must carefully consider. That is a message from this webinar series. With that, let me also go through where we are with respect to phase 3, some of the key aspects of phase 3, which is the development of standard test methods. And that joint industry project is supported by 12 companies. And these are the list of companies. And we, in fact, launched phase 3 yesterday, December 2nd. This JAP had 3 phases. In phase 1, we collected and summarized existing best practices from owner-operators, as well as chemical vendors and suppliers. And I think I interviewed almost all of you in this webinar. In total, we conducted 226 interviews. That helps us to identify 23 different applications across the oil and gas industry in which corrosion inhibitors are used. And then in phase 2, we developed guidelines representing the current industry best practice for corrosion testing. So there are 23 reports submitted to the sponsors. Based on phase 1 and phase 2, we identified 8 laboratory methodologies that needs standardization. That is a focus of phase 3, which was kickstarted yesterday. The 8 methodologies are listed here. In webinar 2, I briefly went over 1 liter rotating cage, why we need to develop a standard test method on the 1 liter rotating cage. In this webinar, I will focus on the rotating cylinder electrode, why we have taken up this issue in our JIP, what are the contributing factors for this RCE, as well as some of the challenges. Every testing laboratory, corrosion testing laboratory I visited and I'm aware of, they do rotating cylinder electrode tests one way or other. This practice started in 1980s when Dr. David Silverman promoted the use of rotating cylinder electrode for corrosion studies. Again, for those who are not familiar, Dave promoted RCE, rotating cylinder electrode, for stainless steel for chemical industries. But because this methodology is easy, produces good results shortly, in a very short duration, everybody, most of the laboratories, almost all the laboratories at one stage use rotating cylinder electrode. Obviously, people are interested in its repeatability and reproducibility. And ASTM, before they started the rotating cage standard test method, they coordinated 3 round-robin tests, one on rotating cage, one on rotating cylinder electrode, one on jet impeachment. The jet impeachment did not go, and the rotating cylinder electrode in 2005, 4 laboratories participated. 4 laboratories are very reputed laboratories from US, Czechoslovakia at that time, United Kingdom, and Norway. Very, very reputed 4 laboratories. They consistently use the same procedure, and this is the data point they got. Again, polarization resistance is inverse of corrosion rate. So that did not meet the ASTM standard in terms of establishing precision. So we restarted understanding what is going on with rotating cylinder electrode. About 3 years ago, many of you were also involved. 13 laboratories from around the world redid the round robin using a different solution, using a different operating conditions. Each laboratory, as per Sheldon Dean's recommendation, did 4 tests, 2 plus 2, 4 tests under the same operating conditions. So 4 times 13 laboratories is what the data point that you are seeing. As you can see here, look at the y-axis. The data ranged by 4 orders of magnitude. RP values range from almost 10 to 10,000. This is in the absence of corrosion inhibitor over a period of 24 hours. Now, how could we depend on this kind of data to select a corrosion inhibitor? And how could we assure that that inhibitor will work wonderfully in the field? So we need to understand the fundamentals, understand what causes these deviations, and fix them so that we establish a good error band or the precision statement. Ideally, that band should be within the green box, or if it is at least within the yellow box, then that is a precision statement that AST will agree to develop a standard test method on rotating cylinder electrode. So until then, we have to question ourselves on the use of rotating cylinder electrode for corrosion testing. People may use it as a kind of quick and dirty or quick method to pre-select corrosion inhibitors, but even then we have to be careful. So what we are going to do in our JAP, and we have put a very systematic study as to what are the variations that could lead to deviations and try to address them. Again, this work will support the ongoing ASTM round robin. I should also point out that in addition to this JAP, various other laboratories, for example, Nikhil Obeshekara from Clarion, he has done lots of tests, shared those data with ASTM committee. And as I said, when you are developing a standard test method, we need collaboration, we need coordination. So we need to put all our heads, knowledge, and experience together to understand why there are variations in rotating cylinder electrode, especially with respect to rotating, especially with respect to carbon steel, and how to minimize them. If we can collectively, collaboratively achieve, then we can confidently use rotating cylinder electrode for our inhibitor corrosion evaluation. Inhibitor evaluation for corrosion control. So in terms of deliverable for phase 3, we will produce step-by-step procedures to carry out tests of all the lab methodologies that will be standardized in phase 3. After the webinar 2, I had a chance to exchange few emails with Milan Bartas. So we are talking about how many variations are there in each one of the laboratory methodologies. Even, for example, if we take rotating cylinder electrode, there are a lot of variations. So hopefully, we'll have one methodology, one design that will be accepted by all the sponsors, and the blueprint of that particular methodology version design will be standardized, and that blueprint will be made available to all the sponsors. One of the most underused, not CAD aspect is the solution preparation. Many of the labs use, let us say, 3.5% sodium chloride. So they just pick sodium chloride, weigh it, dissolve it, and they think that they have prepared the solution. But that is not the most appropriate professional manner. We have to establish various steps even in preparing solutions. So much so that some of the other industries, for example, offshore industries like Navy, Marine, they have standardized solutions for their corrosion testing. For example, ASTM has got a standard for artificial seawater preparation. So don't take seawater from the ocean, but prepare it artificially in the field, in the lab, if you are going to do corrosion testing. Similarly, we are going to establish at least 5 standard solutions, not only how to prepare them, but also the procedure to prepare them, also how to de-aerate them. This is not a trivial task. This is an overlooked task, but this is very, very critical if you are going to produce repeatable data point. So that is one of the side benefits of this JAP. And the ultimate goal is to establish precision of all the laboratory methodologies that will meet the ASTM level of approval. And we hope that we will achieve at least repeatability. We'll achieve precision based on repeatability by the end of the phase 3. Again, we will do it for all the 8 methodologies. Again, this is a cost structure, and again, it's only 5% of the total cost.